Okay, let's start. Um, okay, and today I will discuss research problems related to image colors, and in particular, I will focus on image color correction, enhancement, and editing. And for your reference, you can scan this QR code to access the thesis documentation, and this QR code appears in every slide in this presentation. So, excuse me. So, as the title implies, my thesis includes three related parts. The first part related to or discuss the image color correction, where we focus on illuminant estimation and image white balancing. And the second part is image color enhancement, where we focus on exposure errors occur in camera rendering procedure. And the third part is image color editing, through, excuse me, through white balance manipulation and image recoloring. For each part, we presented in the thesis some methods, and part of this work done in collaboration with technology company through an academic collaboration or internships. Due to the time limit we have today, I will highlight only a few representative work, and let's start. So to start, we need first to define colors, and the colors actually are words we use to describe our sensation of the perception of objects. And this perception includes three major components. The first one is the object spectral reflectance properties, and the second one is illuminant spectral power distribution, and here I'm assuming we have only a single element in the scene for simplicity. And the third one is the sensitivity of our retina's cone cell. When we talk about digital colors that produced by digital cameras, we could replace this sensitivity with the camera spectral sensitivity. And this multiplication, and after taking the integral over the visible wavelength, we got what we call raw image. And this raw image is a linear representation to the incoming light to our camera sensor. And of course, it differs from what we used to see when we take a photo, and we used to see something more beautiful, like what we call display image. And this display image actually results after some processing to this raw image, and usually rendered in some standard color space. And in this presentation and in the thesis, we assume it's a standard RGB or sRGB color space. So that is, when we take photo, camera image signal processor or camera ISP applies some steps to render the raw image and get the final sRGB image. And from this camera ISP standpoint, we will focus on some components in the camera pipeline that contributes in the quality of the final colors. And also we will discuss possibility of fixing some errors that may occur during this rendering procedure. So let's start with the color correction. And I will focus right now on the illuminant estimation. And more generally, raw image white balancing is a process applied to all raw images we have when we take any photo. And it aims to remove any unwanted color cast caused by the scene illuminant. And it's applied too early in the camera pipeline to the raw images, and afterwards, cameras apply some photo finishing procedures to get the final sRGB image. And we can think of the problem as follows. We have some scene RGB colors, and we have a global and single scene illuminant color that multiplied by this scene RGB image, and that results on what we have in the raw RGB image. Given this sensor raw RGB image and the sensor illuminant color, and we can simply retrieve the scene RGB colors using a simple diagonal operation. And this diagonal operation is applied to scale each color channel independently, as shown here. In reality, we don't have this scene illuminant, and there is an illuminant estimation algorithm should run on board cameras in order to get this estimated illuminant color. And of course, we need some mechanism to measure how accurate this algorithm is, and we usually compare that with some ground truth obtained by having any calibration object in the scene. And here I'm showing a color shaft object. And we used to use angular error to measure the differences between the estimated illuminant color vector and the ground truth color vector. We can categorize the illuminant estimation into two different categories. The first one is the statistical methods, which are simple, easy to implement, but less accurate than the learning methods, which are more accurate, but generalize poorly for new camera models. And I will come to this point later in the presentation. So if we have a look into the statistical methods, they are usually based on some hypotheses or assumptions, and the most common one is the gray world assumption that assumes the world is gray. So to get the rough estimation of the scene illuminant color, we can simply take the mean of RGB values. And it works perfectly well for many scenarios like here, but it can get fooled with some tricky scenes like that. And in order to see how bad gray world works in this example, I'm gonna show the correction using like more accurate or ground truth illuminant color. So you can see here the correction with the ground truth illuminant and the correction with gray world. So for this accurate results, people start thinking of using some advanced methods instead of those statistical methods, and mainly people start to discuss using deep neural network or DNN in order to do the estimation process. And such DNNs or any learning-based method usually learn the mapping between the training raw images and the corresponding illuminant colors. And if we plot this illuminant colors in the RG chroma space, we got this curve shape distribution. One may think that this curve distribution is universal over all cameras, and it's very easy task to train a single DNN model for illuminant estimation. That's true in reality if we work in some canonical space like CIE XYZ space, and that shape what we call Planckian curve. But in reality, we don't work in any canonical space. We work on the camera sensor raw space. And if we plot the color distribution of the illuminant colors of some set of scene captured by different camera devices, we will get something like that. And that makes sense because the camera sensor response function contributes directly in the image formulation of raw images. And we already mentioned that earlier in the presentation. So that means if we capture the same scene with two different camera devices that have different sensor spectral sensitivity, we expect to get different measurements. And consequently, we have different ground truth colors. And that makes the DNN solution less empirical in reality, because if we train a DNN solution to, like a DNN model, sorry, to do the illuminant estimation for sensor X, we decided to deploy this DNN model on another sensor. Let's say here sensor Y. We need to collect a new data set captured by sensor Y and retrain or tune our DNN model. This is a very tedious process, and that was the motivation for our first work here, which is sensor-independent illuminant estimation, where we need to deploy develop some DNN-based illuminant estimator, but still be sensor-independent. So the idea here is we try to learn a working space that do kind of canonicalization of any incoming image taken by different camera sensors. And this working space works better for the illuminant estimation task. So in particular, we train two subnetworks jointly. The first one aims to map the incoming images into our working space, and the second one do the illuminant estimation task. So if we start with the raw RGB image, and we go with a differentiable histogram block, we got the histogram of the color distribution that represent the colors in this image. And inspired by prior work by John Barrow, this feature is super powerful for the color constancy or the illuminant estimation tasks. So we start from this histogram feature, go with the sensor mapping, very simple neural network to predict the 3x3 matrix. And this 3x3 matrix that we assume it does the mapping task, it will be multiplied by the raw RGB image to get what we call mapped image in the working space. And from this mapped image, we do the same thing, we get the histogram feature and then go through another illuminant estimation network to produce the 3D illuminant vector. So this vector represents the color, but in the working space. So in order to get the final RGB vector or illuminant vector for this input image, we need to project it back to the sensor space by multiplying this by the inverse of the mapping matrix. As every step here is differentiable, we could train this framework in an end-to-end fashion, and that means the sensor mapping network will learn to project the incoming images to a working state that works better and helps the illuminant estimation step. We evaluated our method using leave one out cross validation on 3 different data sets that includes 11 camera models, and we achieved better results than all sensor independent methods, which are mainly statistical methods, and we achieved reasonable results when we compare with the sensor dependent methods. We have to keep in mind that all those sensor dependent methods require retraining when they are deployed to new sensors. So now I will discuss the image white balancing in sRGB space. And in particular, we are interested in fixing colors for improperly white balanced sRGB images. So recall that white balance applied early in the camera pipeline and followed by this nonlinear steps under what we call photo finishing processes to get the final sRGB image. And we need to remember that those photo finishing steps are camera specific and aim to produce pleasing photographs rather than rendering accurate scene colors. Which means if we capture the same scene with different devices, we expect to get different colors. And that also means if we think of undoing the camera photo finishing step, this is impractical idea because without having an accurate calibration, we cannot undo this nonlinear process to get the raw image and do the white balance correction there. So what we can do with image like that, rendered with some white balance errors in sRGB space, one may think of just selecting any neutral or achromatic reference point that represents the illuminant color in the scene, and then adopt the diagonal solution that intended to be used in raw images. And when we compare this result with what we got when we apply white balance correctly in raw, followed by applying the nonlinear ISP operations to get the final sRGB image, we can see the difference between this diagonal collection of sRGB colors and the ground truth if you apply the white balance correctly in raw image, followed by the full rendering process. And that's what we try to achieve in this paper. So to start, our method is data-driven, so we need to design an accurate, or like to generate an accurate data set that represents our problem. And as we know, the problem occurs early in the raw images. We start with rendering raw images with a camera ISP emulator that mimics the camera rendering procedure with different white balance and photo finishing steps. So that gives us for each raw image, we have different versions of the same scene rendered with different white balance and sRGB space. And also we could generate the ground truth by manually select an achromatic reference point. So that gives us a pair of images in sRGB space, one with incorrect or inaccurate white balance rendering, and the second with the ground truth. Then we compute a mapping function that maps the colors from IT or the input image and the ground truth, and that can happen using the standard least square fitting. So this mapping actually aims to project or map the colors of the input image to be very close to the colors of the ground truth. And this mapping done using this kernel function phi, which is a polynomial kernel function that projects the 3D RGB vector into a higher dimensional space. Please pay attention to this part because I will mention that later in my presentation. So we also, instead of just rely on the spatial or semantic information in the image, we followed the same idea of using the histogram feature, and this histogram feature is projected using PCA projection. So we did that for many images, and that give us our data set that includes 60K images. And from this 60 or over 60K images and their PCA projected feature, we build our model. So our model includes only, or like require only 20 megabytes of memory to run, and it includes the PCA projected features and also the mapping between improperly or incorrect white balanced images and the corresponding ground. We store that for all images we have in our dataset, and all of that require only 20 megabytes. So given a new image captured by unknown camera and unknown white balance setting, we generate the histogram feature and then generate the PCA feature, search it for the similar examples in our training set, and then we blend or linearly blend between the pre-computed correction matrices to get the final corrected image. And it works perfectly well, achieve the state-of-the-art result when we compare with diagonal solution in sRGB space, and generalize very well for images outside our training dataset. Here I'm showing a qualitative comparison between the diagonal solution and our result. And please see chapter 6 in the thesis for additional results. So now I will discuss the image color enhancement part. And as I mentioned earlier, we interested in seeing exposure errors. And in particular, we are interested in under and overexposed scenes and how to correct them in sRGB space. So here I'm showing two examples of under and overexposed images, and we have to remember that those images are in the 8-bit sRGB space, not in the raw space. And we may think of using a traditional like image enhancement tool like Photoshop HDR tool, and that doesn't work as expected. And that doesn't work actually because the exposure error happens early in the camera pipeline through three different factors that camera uses to adjust the exposure, which are the aperture size and capture shutter speed and ISO value. And all of those three factors contribute directly in the construction of the raw image. And that could result in some dark raw images and consequently dim sRGB images, or some overexposed or very bright raw images and sRGB images. So here I will go with the learning multi-scale photo exposure correction. And as a teasing, I'm showing our results with under and overexposed images, and those images are from Flickr, so our method generalizes very well. So we start, our method is learning-based methods, so we have to think about the data. One may think of capturing a realistic or like a real pair of images, one with proper exposure setting and one with some exposure errors, but that will limit us for like certain type of scenes, like indoor or lab setting scenes. So instead, we decided to synthesize this exposure errors in sRGB space. So one may think of using simple gamma operation or scale operator in order to mimic over or under exposure errors. But when we visually compare those images with what camera produce when it has some overexposure error, we can see the difference. And that motivated us to generate our own data set starting from raw images. And we follow the same procedure. So we start from MIT Adobe 5K dataset and start with the raw images, apply some digital exposure, and go with the camera ISP emulator to get the final sRGB image, but with different exposure settings. So that gives us different exposure, exposed sRGB images. And for each set, we also have the ground truth, which manually rendered by expert photographer and go through the camera ISP emulator to put the properly exposed image. And that gives us over 24K images, and compared with other available dataset for the exposure errors, like the LOL dataset published in BMBC 2018, our dataset covers broader range of exposure values or errors, and it comes with properly exposed ground truth, and finally it was rendered in more realistic way that very close to what happened in reality. And based on this data set, we built our multi-scale neural network framework based on the Laplacian image decomposition. And our method starts with the first level of the Laplacian pyramid and process it in a sequential manner until we get the final result. And we use pyramid loss, reconstruction loss, and adversarial loss to improve the perceptual quality of the final result. Here we achieve better results than a Vellum solution to fix overexposed and underexposed images. And when we test it on images outside our training and testing, of course, training and testing data set. And here I'm showing examples from Flickr with real exposure errors. Our method achieved much better results than recently published methods for image enhancement like DCE. So now I will discuss the last part, which about image color editing. And due to the time limit, I will only focus on the white balance manipulation, and you can check the thesis for the image recoloring part. So white balance editing in sRGB or like in post-capture time is required in many scenarios where the user try to capture a particular scene, but the auto-white balance algorithm that run on board camera ISP produce something different than the user preference. So in this case, maybe in post-capture white balance editing tool may help. So recall that in CVPR 2019, we proposed this KNN framework based on the polynomial mapping. And when we submitted this paper to CVPR, reviewer 2 suggested that maybe DNN would be a more interesting solution. So that motivated us to do the deep white balance editing, which is a deep framework encoder-decoder that maps any incoming image in sRGB to the corresponding auto-white balanced image. But we not only do the auto-white balance, we also append two different decoders to provide the user with additional white balance option to make things more interactive. So in testing, the user can select any one of the decoders and produce different results. And here I'm showing an example of input image and the auto-white balance generated image using our method, and the other two white balance options, which are shade and tungsten. So the reason we use this shade and tungsten white balance is that those the correlated color temperature spans the commonly used color temperature in the Planckian curve. And in testing, if the user prefers something in between those two different color temperature, we can simply interpolate between those images to give the target output image with the target color temperature. And the fun fact is that when we submitted this paper, next year to CVPR, reviewer to say it's the same last year paper but with deep neural network. So to make reviewer too happy, we developed color temperature tuning, and in particular, we did two different things than the deep white balance editing. First one, we didn't submit it to CVPR to make reviewer too happy. The second one is it's not a deep learning framework, and it relies on a very simple modification to the camera ISP, achieving much accurate results compared with any other solutions. So recall that for the standard camera ISP, we start with some raw image and the color temperature that is either selected by the user or suggested by the auto-white balance algorithm. And we go through the camera pipeline standard processes to get the final sRGB. This is the standard camera ISP. So what we proposed is to have a very tiny version of this raw image, almost less than 0.5% of the full-size image, and go with a fixed preset of color temperatures or white balance settings that render this image with the camera pipeline to give the final sRGB versions of this tiny raw image. And then we can simply subsample the original image and do the fitting before releasing the final JPEG file. So this fitting keep in mind that we are interested only in the coefficient of this polynomial fitting, which is require less than 6 kilobytes. And this small metadata can easily be stored as a metadata or JPEG comment in the final JPEG image. In testing, and let's assume the user decides to change the white balance settings, we can simply load up the metadata and apply that to get the final corrected image. And similarly to deep white balance editing, if the user prefer a target temperature that is not included in our presets, we can simply interpolate between the closest or nearest color temperature values we stored to get the final image. It runs super fast and it can run in real time. And more importantly, it can run in post-capture stage to do the white balance or color temperature tuning. So, to summarize, I discussed topics related to image color correction, and I discussed our sensor-independent methods. And the first work proposed to fix sRGB image white balance errors. And then I discussed the image enhancement part, which includes or focuses on fixing exposure errors. And then I discussed the image color editing part with white balance editing. And although it's not covered in this presentation, but it's included in the thesis, we discussed in the thesis image recoloring methods, where we propose to auto-recolor any input image using the spatial information or semantic information of this image. So future work should include something related to deep learning in camera ISP. And like in the recent 5 or 6 years, people start discuss methods for deep learning that target particular tasks in the camera ISP. And for example, you can see something like it proposed to replace the classical image processing or computer vision method used for image demosaicing with any DNN network. And we can do that for any other step in the camera pipeline, like white balance or any detention step. But before going with this direction, we have to keep in mind the computational power that is very limited in camera ISP hardware developments. Either we use deep learning or classical methods to do the tasks in the camera ISP. Behind every camera ISP, there is a lot of tuning procedures or like processes happened in order to make things work. And recently, people start to discuss a solution to get rid of all of this tuning by training a single neural network that can do the camera ISP job. And before going with this research direction, we need to think, does this really help or not? Because in traditional supervised learning, we need some target ground truth images. And in many cases, it should be something generated by another camera ISP. So what is the upper bound of this single DNN ISP, like in terms of the image quality, let's say, and how we can deal with any failure case compared with the traditional camera ISP, where we can diagnose every step. So before going with this direction, I think we can think more carefully, and we need to consider maybe something to make this camera ISP not only render the final sRGB colors, but more smart in the way that may include some user preferences in the final rendering procedure, or maybe like make this camera ISP invertible to reconstruct the raw image at any time in post capture time. Another research direction could include multi-element color constancy, and in many scenarios we see something like that, where we have indoor and outdoor lighting in the same scene. We already discussed methods to deal with that in an interactive way in the thesis, but in more complex cases like that, we may think of we may need something more interesting that can do the auto white balance procedure per pixel. And the problem here is that if we take any random pixel or patch of this scene, for example, we will find every single pixel or patch got affected by many mixed element sources. And to mimic this realistic situation and generate a realistic data set to evaluate or train a model, we need maybe think of some computer-generated data sets. And the last thing is maybe the overexposed image like this, which suffer from like very hard overexposure error, and all the details are gone. We already discussed the method for overexposure enhancement, but in this cases, our method should fail because it requires a huge amount of hallucination or impairment. And in these cases, we may think of including some semantic information in this scene to get different treatment of different region. And for example, like we can have any reasonable image completion part for the color, for the sky or the tree, but for like objects like faces, we should be more careful because it's very risky. So you can imagine that you take a selfie with overexposed errors and an algorithm suggests another face instead of your face. That's not accepted at all. So finally, I would like to thank my supervisor, the supervisory and examining committee, my collaborator and lab mates, and thank you everybody for attending. So I'm happy to answer the questions.